Thank you for coming to this session. My name is Serge Leef. I am a DARPA program manager. I came to DARPA 3.5 years ago from EDA industry, for many years at Mentor Graphics, and prior to that, Intel and Silicon Graphics. So at DARPA, I work on next generation EDA, secure silicon, domestic microelectronics, and a number of other things. But mainly, my focus is next generation EDA. So what I wanted to talk about today was the digital simulation and where should it go. We sort of know where it is, but where should it go is a more interesting question. And as like all other EDA technology, this has sort of been driven by customer applications from the beginning of the industry. So in the 70s, the design automation requirements were driven by military and aerospace. Then in the 80s, a microprocessor emerged, and suddenly we started producing more value in software than hardware, or actually started producing value in software. Hardware was always there. Then in the 90s, we saw the emergence of telecom, datacom, and here we now had two processors. We had a control-oriented processor and a data-oriented processor, so two streams of software. And then consumer market started dominating the demand space. And now in the early iPhones, and I don't know if that's still the case, there was like 11 ARM cores, and this probably is still like that or worse. So many streams of software and many hardware compute instances. And then systems started driving advances in this area. Now you have a modern vehicle that has several hundred onboard computers that are performing control of physical systems. And so where is this all going? And so my view of what is happening right now is that the next generation of advances is going to be around this notion of computational continuum. And so what I kind of anticipate is that people will be building vertical applications that will have the edge communicating through 5G through the cloud. And just about everything that you come in contact will have this type of footprint. The only question is how much compute happens on the edge, how much on the cloud, and that would be application specific. And so we looked at the progression of the chips and the sizes and the growth of this of the transistor counts over the years. And so EDA has been riding on the coattails of Moore's law for quite a long time. So the performance improvements that we've been able to deliver sort of relied on the underlying computing. And so the innovations in design automation, in my opinion, have been largely linear. Like for instance, if you look at simulation today, the events are probably evaluated more or less the same way inside the simulator as they were in the 80s. And so what has happened is in the simulation or functional verification market, people have advanced the technology by functional aggregation, by adding test benches and assertions and basically a bunch of stuff around the simulation. And so to me, and this may be a mildly controversial statement, the last significant advance in EDA industry was in 1988 when Design Compiler emerged. And so this is coming at a time, this realization that there has been no innovation in the industry. It's coming at a time where designing modern chips is becoming more difficult and more expensive. So back when I worked at Intel a long time ago, we had this concept of a tall, thin designer. This was a person who could go from algorithms down to polygons. And we believed at the time there were about 5,000 people in the world who were like that, while there were 50,000 software developers in the world. So this was in the 80s. Right? So if you look at this now, I would assert there's still only about 5,000 people in the world that know how to do this. But now we have probably 500 million software developers. So the ratio of technology advances has sort of shifted. And you look at computer science majors dramatically outnumbering the EE majors in universities. So what's going to happen here when it will cost $500 million to design a chip at 5 nanometers? So all of this are unfavorable trends. So you'll see a lot of charts in my presentation from 2009, 2005, and even the 90s. And this is a trip down the memory lane. As I started thinking about this presentation, I sort of realized, a lot of problems I was talking about in 98 are still unsolved problems. And so if you look at how people design systems, this is a slide that I created back in 2009, and it's still approximately true. So you basically have system is architected, hardware people go their way, software people go their way, and partitioning decisions are made early on and without a lot of data. And then they encounter the timing closure loop, where it takes unknown amount of time to get to closure, and then they encounter integration and test phase, where it takes unknown amount of time to get hardware and software to work together. But the interesting observation relevant to this particular topic is that functional verification, I said in 2009, is trained by even today's designs. And so how do you verify multidiscipline systems today with billions of gates? So, even though software is a key to all of these systems, the differentiated functionality, it has participated only minimally in functional verification. People use it to drive, to represent test benches and to some extent software in a loop emulation, but really the entire software stack, I'm not sure gets simulated ever. And so back in those days, this graph was interesting. So what we saw was that the number of gates becoming available was growing very quickly, and number of designers needed was sort of expected to be growing along with the gates. But what we noticed is that the humans were not actually becoming any smarter. And so the productivity of design engineers has not improved with this trend. And so the natural reaction to all of this was, so now we need to build chips out of multiple components, multiple pieces of hardware and software IP, and that's how we're going to deal with this productivity gap. But in reality, we created a whole new set of problems, because now we have all of these items that need to come together in order for the system to work. I still remember a visit to a wireless subscriber side device company in San Diego one time, where I was in this building where there were 800 engineers in that building, and I had my kind of uncovering meeting with them, and I was trying to understand, so what do they do in this building? And so I was asking, are you guys doing the baseband processor here? I said, no. Are you doing the middleware? No. Are you doing the operating system? Are you doing applications? After a while, I ran out of theories as to what they could be doing in this building with 800 people. And it turned out all they were doing in that building is integration of various pieces that they were getting from the other parts of their company. So this integration consumes majority of the time on SoC projects, and that was true in 2005. Still true today. Probably an average SoC, 95% of the real estate is occupied by things that are reused. So what happens now? This is a chart I got and have been reusing. So this kind of shows where in the design process on the right the energy is spent as people are designing modern chips. And if you look at what is projected for 5 nanometers, this chart asserts that it's going to cost $500 million to design a 5 nanometer chip. And I'm assuming, high gate count, high complexity. And even if at the trailing edge of this chart, we're still talking about $30 million to design a chip on 65 nanometers. And so what that does is it impacts funding for the startup ecosystem. in fabless design companies. So the conventional venture capital worldview, I guess, is to give people $500,000 of seed funding so they can shape their proof of concept, and then another $3 to $5 million maybe to build a working prototype, and then in the B round, $20 million when they start engaging with the customers. That's all fine for consumer web companies, but when you look at the semiconductor companies, you start seeing something different. You start seeing that it takes $20 to $30 million to get to first working silicon, and no venture capitalist would really accept this. The thing is, I was on an advisory board of a fabless semi company and spent a lot of time dealing with VCs, and they complained profusely the whole time I knew them about how did they get snookered into this semiconductor startup, because for this kind of money they could have had 40 internet plays. You know, so they got in there and they regretted it. And now, when I see venture capitalists who are investing in fabless semiconductor companies, unless it's AI on the edge, which is fashionable these days, they're clearly insane, because this makes no sense. Venture capital in this context is a game of numbers, because the success rate is like 3 to 5% at best. So you want to spread the money widely. So, EDA has been around since the 70s, and we've progressed in functional design, physical design, and verification. And so where is EDA research to go now? So, what's in blue is my answer to that question. So as somebody who has a charter in DARPA to advance EDA, to energize EDA, this is what I'm investing in. So I am essentially working in this 4 areas. One is platform-based design, where you can create accelerators, do so automatically, and do so even during the mission. So this big thing in Department of Defense is something called mission reconfigurability. So it isn't just figuring out what's the optimum partitioning between hardware and software where the accelerators are needed, but what if during the mission you encounter an opportunity to have something accelerated or throughput improved and so on. The second area where I am focusing is system synthesis. So here we're doing automatic integration of IP into platforms. We are focusing on optimizing synthesis in the next generation, not just on performance versus size, but also performance, size, power, and security. So security becomes a dimension in the optimization story. And we're also working on advanced simulation. So clearly there has been something interesting that happened with the emergence of the cloud. Cloud gives us infinite compute and infinite storage, and yet digital simulation really hasn't figured out how to take advantage of this. Another anecdote here, my first day at Mentor in the 90s, I was introduced to this guy who was working in this darkened office, and I was told not to disturb him. But eventually he came out of his office and I talked with him briefly, and he told me that his job, he was responsible for the innermost event loop inside QuickSim. And he said that he has been working on figuring out what's the minimum number of machine instructions required to evaluate a single event. And he arrived at about 30. And he believes that he had reached limits of simulation physics. And it was impossible to go any further. And what I've been learning lately is it turns out that is still limit of simulation physics. If you are trying to evaluate events, that's approximately what you have to spend in terms of machine instructions. And so, and that, of course, is related to the fact that the way people think of simulation is they build a directed acyclic graph that ideally needs to be in the contiguous memory. There's terrible data locality property associated with this thing. So it's not easy to distribute simulation. But I have some money on the table betting that people can come up with fresh ideas in this area. Okay, so I would like people to rethink this medieval event evaluation approach in the context of the cloud, which offers infinite compute and infinite storage. So I am going to try to encourage innovation in this area. So how can we linearly or hyperlinearly scale simulation on the cloud? And of course, there's only kind of two ways to speed up simulation. One is to make events go faster, and the other is to reduce the number of events. And so here is where I think there's a good opportunity for machine learning. Can we create low accuracy, high performance surrogate models that are abstract, not really detailed, and yet are sufficient in a way to interact with the rest of the system to give us interesting insights? And the other thing that's sort of fascinated me since the 80s is the notion of speculative parallelism. Particularly in the late 80s, there's algorithm that was widely publicized, time warp. And so I am very interested in revisiting this, and there's some exciting work that's going on in taking a fresh look at that and implementing that type of approach in hardware. And then lastly, there's secure silicon. So what my group is focusing on is synthesis of on-chip security engines that can be scaled with the economics of the particular chip, and multi-layer security and depth strategies in silicon. So back in fact, I just ran into a guy on the floor here that created this diagram back in 2003. And I thought, okay, so we keep talking about no human in the loop and machine learning enablement. This was the dream diagram that we drew back in 2003, and we thought, okay, so the way that the process can go is that you assemble the platform by dragging and dropping things, and they snap into the bus. You get bus interface hardware, and device drivers get auto-generated. Then you subject it to SOC level simulation. Then you extract all kinds of histograms that highlight where the resources are consumed, whether the resources are software or power. And then you essentially automatically extract those high-cost functions and turn them into hardware accelerators. And then you do it again iteratively. So that was our thinking back then. But now, if you sort of think about emergence of AI, why do you actually need a human in the loop here? Why can't you unite this type of flow with machine learning techniques? And if you think about it further, you can say, yeah, that potentially makes sense in some of these cases. But where we're still left is that we need very, very fast simulation or ability to evaluate architectures to support this flow. So I'm back to my original complaint that the simulation hasn't advanced. And so what do we do to rethink digital simulation? This is another graph that's as old as time, where we see that the design productivity and simulation are diverging. It takes a lot of effort to verify things, and relative to design effort, there's a verification gap that's been there. And the simulation techniques, as I said, I don't believe have changed appreciably in 30 years. And so if you look at this year by year, the amount of time spent in verification is actually not getting better as you get closer and closer to now. You see that more and more time as percentage of the project time is spent in verification. But you'll say it's not so bad. Simulators have been getting faster and faster over time, but they've been getting faster because the underlying hardware on which they run has been getting faster. And our PCs have benefited from Moore's law enabling faster and faster computers. But the thing is, where we got now is the number of transistors we're putting on the chip is continuing to grow, but the kind of underlying architectures we're running on are no longer giving us 5 gigahertz or 8 gigahertz where we get extra performance for free. Now people put many cores on the chip, and the exercise of taking advantage of all those cores is still left up to the student. So thus, we think that post-Moore, the architectural direction is multi-core or cloud. But modern simulation algorithms are not at all designed to take advantage of such worldview. So this is kind of all the stuff in gray is other investments that we're making. But what I wanted to highlight is what we are focusing on. So, so we're kind of, our starting point is Verilator, which is a plausible open source simulation technology. We're looking at adding some things to it to make it comparable to or on par with state-of-the-art commercial simulators. But that's not the interesting part. The interesting part is what happens from here. And from here, what we're trying to do is exercise these techniques that I have mentioned earlier. So for example, instruction level abstraction, so the abstraction play, I'll talk about this a little bit later. And event reduction play, the surrogate models, and cloud scaling, and HPC that leverages the speculative parallelism. And we think all the combination of these things is, should lead to the next generation digital simulation. So, so what we really want to do is we want a convergence of technologies to drive the next generation simulation. So we think that the next level of abstraction is one of the legs of this stool. We think that reduced order models or surrogates is another element. And then speculative parallelism is the third element. And then lastly, all of this needs to be cloud scalable, okay? And then how do you partition the designs across the cloud? Well, maybe this is I know EDA has been looking for a good application for machine learning, and my observation is he hasn't found it yet, so maybe partitioning is something that can be taken advantage of. Also, the cloud now has FPGA instances, so can they be leveraged? Can the programmable hardware be brought into this octopus-like strategy? Maybe. So I'll talk about instruction level abstraction, and I'm pleased my friends from Princeton are here, who are the ILA folks over there, and they have a seminar this afternoon at 1:30. So people who want to learn more about ILA can go there. But basically, we know instruction level simulation is fast. Instruction set simulators existed forever. We know they can run really fast, and we model processors that way. And then, you know, the thing is that the resolution or accuracy or detail of simulation really is kind of driven by timing. So if you were to do logic simulation, you typically can guarantee that timing to be accurate on the clicks of the clock. If you go to RTL simulation, typically on cycle boundaries. And then if you go to instruction simulation, the accuracy of the system occurs on instruction boundaries. So the approach that we're interested in, that's advocated by Sharad and company, is the notion of treating all the peripherals inside the design as instruction processors. So in other words, if you have a bus-based peripheral that receives memory-mapped I/O messages, you can think of them as instructions. And so now you have, each peripheral turns into a machine with a relatively narrow instruction set. And so if you can start thinking about everything in the chip as an instruction processor, there are opportunities for speed up at the block level. And so what you can do is you can go from this situation where you have you know, a CPU that you are simulating as an instruction set model, and that runs 5 megahertz, and you have a memory that can also be modeled very fast. But your RTL, your original design, is still running at 10 cycles per second, and all the third-party IP potentially too. And you may have some fast models for some of your IP pieces that makes the situation a little better. But in general, it still sucks. So what if we use this instruction level abstraction technique and could convert all the peripherals that we have in the system into this ILA abstraction? So we now have a framework of a bunch of instruction level simulators where we could theoretically push the performance of the whole session further. So obviously abstraction is something that's been talked about in our industry for, from the beginning of time, and so this is to some extent like a novel look at where else can we go with abstraction. The other thing that we're doing that's interesting and relevant here is high performance computing. And so back in 1988, when time warp was advocated, the idea was that you divide your design into multiple partitions and let them all run free forward. And if one partition received an event from another partition that arrived behind where the time has already advanced, then a rewind had to happen and so on. And so this, I personally experimented with this when I was in the industry, and it worked pretty well for cycle and instruction level simulation, but it was terrible for event-driven simulation. Just didn't work at all. And so that's why we were kind of pleased to see that there's renewed activity in this area, particularly at MIT, where they have substantially reworked the time warp strategy, and in the way they assign nodes to different compute partitions. And so they have created a technology called Cronus, and their technology is implemented as tiles that they can map into an FPGA. And what they've been able to demonstrate is linear performance improvement with the 16 tiles that they have originally experimented with. So we got involved with this, and we're working with them to see, so how many tiles can you actually put on a single chip? And where's the linearity? Where does it end, or does it end? And then what if we were to put a bunch of FPGAs together? Is it still linear? Or what if we were to implement this on a standalone ASIC and then replicate this ASIC 1,000 times? And what if we were to take an instance with thousands of those ASICs and replicate it 1,000 times on the cloud? So the question that we are studying here is to how far can this type of strategy be taken? The reduced order models is another thing that we're thinking about. And so if you look at the same kind of diagram that I showed earlier, what you're really interested when you're doing simulation at a full chip level is you want to answer two questions, really. One is my original design that I'm adding to this bunch of third-party IP blocks, does that work as I expected? And the second thing is, does the whole system work as a system? And so for that, I don't really need hyper-accurate and slow models of the other things that I'm not really adding value to. And so the observation was made, strangely, we heard about it from industry other than digital design, is why wouldn't we consider creating something called surrogate models? Surrogate models being essentially ML-trained models that you can derive from a real model. So let's say you have a slow RTL model of a peripheral that runs at 10 cycles per second. You can apply to this thing, 1 million vectors, and then use the inputs and outputs as a training data set. And then essentially train a surrogate that can be approximately like that peripheral, but approximately may be good enough for it to play a supporting role in the SoC simulation. And this picture shows the black box training strategy, but what if you were to also analyze the internals of the RTL model? What if you were to also analyze the traffic that goes in and out, instead of just ones and zeros, recognize protocols and packets of things that are being sent? And so that would result in faster training and higher accuracy surrogates in less time. And where we encountered this, interestingly enough, is I was visiting a jet engine company. And as you may know, jet engine has hydraulics and magnetics and electrical and software, just a really, really complicated thing. And these people insist on simulating the whole thing. And so what they've done is they've created surrogate models for some components, all components actually. And if they're interested in simulating the stresses on a blade of this thing, they turn everything in their simulation into surrogates, and only the blade is fully modeled as a mathematically correct physics model. And that's the only way they can simulate this incredibly complex multidisciplinary systems. And so that's sort of where we started making a connection. Wait a minute, in digital design, we live in a much simpler world than that. Can't we also explore the notion of surrogate models here? And so, so multiple approaches, in my opinion, need to be combined in order to enable next generation simulation. The abstraction, speculative parallelism, reduced order models, and significantly cloud scaling. So just a few more words about the reduced order models. So the way that we sort of think about it is any system can be viewed as consisting of two partitions. There's the design under test, and there's a bunch of stuff that surrounds the design under test. And this non-dot models really don't need to be accurate enough to support system-wide simulation goals. And essentially, what we would like to do is to create the type of simulation where the design under test is simulated fully, but all the other stuff that surrounds it is, in fact, a surrogate. And so the objective here is to speed up simulation of microelectronic systems by essentially generating trained models. Now, in digital design, the surrogates can be created by taking like RTL model and training a surrogate. But if you think about like system simulation, for instance, what if you already have an ECU and you know what messaging traffic goes in and out, and you already know how it interacts with sensors and actuators? What if you could collect physical data from running this thing in real world and then use that to train a surrogate? So that's actually something that we're also exposing. What we found is that the second generation AI was actually insufficient for the task that we were contemplating. And so this effort focuses on something called third wave AI, where the machine learning models are composable, meaning you can create hierarchies of ML trained models, and meta-aware, in other words, aware of something other than their unique inputs and outputs. And that's what we're advancing in this context. So the way to think about it is relatively straightforward. If you look at the SoC, on the left, we have a bunch of IP blocks, CPU, memory, I/O, and then we have the design under test. So what if we were to take everything but design under test and turn it into surrogate models? And then this chip, in turn, lands on the printed circuit board, where it's surrounded by a bunch of analog components, for which we also don't have models. Maybe we can have surrogates for those too. And then this board becomes an element in the electronic control unit inside a car, or LRU inside an airplane. And now, what if we had the surrogates for the other things in this vehicle? And so you could essentially think about what we're doing here as turning these things into surrogate models, either standalone ones or the ones that we can lump together, because the distinction between them becomes less and less important. And this is where composability of the third wave AI comes into play. And so since I mentioned cars and airplanes, I think I kind of have to go there for a second. And we're talking about simulation. This is not exactly the functional verification or digital simulation, but still, I thought it was worth noting that in the concept of this revisionist surrogate model thinking, there are some things that start to become possible. And so what people do when they build large physical systems like planes and cars is they actually build prototypes. Simulation is kind of foreign to that community, or at least simulation at the level of fidelity that gives you actionable insights. And these people typically build prototypes, very few prototypes. They cost a lot of money. And then multiple teams compete for access to those prototypes. And at best, they are able to execute few mainstream scenarios and not much else. And if you are cognizant of modern vehicles, you know that there are hundreds of onboard computers and all kinds of things can go wrong. We know in modern digital chips we're through simulation, we're covering maybe 3% of the total space state. Now imagine an S-Class Mercedes with 300 onboard computers and a gig of software with each one. How much test space are we really covering by driving this around Sahara for 3 months and Alaska for another 3? So not much. And so, the ideal thing is that if you could take each element in a distributed system and be able to simulate all of its elements, including the silicon platform, embedded software, network interface, and the multi-physics plant that it controls. But the reality, of course, is not that. The reality is that we have domain-specific simulators with walls between disciplines, and we can't really do this at all. And so the question then becomes is, how do we do something really profound to advance the state of the art of simulating the full vehicle? So at DARPA, every conversation starts with literally like 25 words or less, what, why, and how. So like if you think about the Kennedy call for action for moon landing, put a man on the moon, in 10 years, money is not mentioned in that call for action. Neither is it here. And so this is the program that I'm developing. And so what I'm trying to say here is I would like to be able to execute meaningful scenarios at near real-time speeds, at near zero modeling cost, and gain actionable insights. So this is very DARPA-ish call for action. Now remember, DARPA focuses on year 2030. Not next year, not 5 years from now. So aggressive things like this, I actually found cause a really interesting reaction in the community, and people start becoming really creative. I already had one program that I floated where I thought, this is crazy. There's no answer to this question that I'm going to float to the community. And we were stunned by getting like 11 proposals that propose strategies that we have never contemplated on my team. So I am hoping that it's going to cause a similar type of creative thinking. But the other element of specifying a program is that I have to prove to the community that there's at least one way to skin the cat. So this isn't totally insane. And so basically, my theory is that it can be done if you take the software that's supposed to run on each electronic control unit, abstract it away from the actual hardware, and create a notion of a virtual ECU. So this is ECU that's devoid of personality and runs basically as an interpreter on top of your underlying architecture, maybe x86 or something like that. And then this virtual control unit can be personalized. So you can take and provide a resource model type of description that says it takes this many units of time for it to do X, and it consumes this many joules of power for it to do Y. And so you can provide resource information, and this resource information can be an estimate by a human, it can come from a data book, or it can come from a surrogate that's been actually trained by a simulation model, or it can come from a real physical device experiencing real traffic. In fact, I have one of my performers using a real hybrid electric bus that they've been running in Europe, and they're collecting 10 hours of training data at a time every time they run it. And so I have this activity going on right now and showing actually phenomenal results in terms of building surrogates based on data collected from real operation. And so the point of this VCU, though, is to control interface to real world. So then we need to have an interface to sensors and actuators. But creating a complex model of a mechanical system defeats the purpose of going fast. So why don't we just stub it out? Why don't we replace the anti-lock brake system with 10 C functions that basically say, okay, it's now locked, it's now activated, now wait 27 milliseconds and do something else. So a stub that we do commonly in EDA. Or you could take a real mechanical item and train a surrogate for it, so that you would have a fast surrogate that represents the mechanical thing. You can do similar things with a human. Human is one of the biggest unknowns in this type of systems. God only knows what a human can do. But if you think about a human driver, how many things can you really do? You can turn the steering wheel by some number of degrees to the left or to the right. There's finite number of buttons that you can press. There's 2 pedals. So, you could probably distill this down to a small C program that says the driver goes to the drugstore, and that's the series of actions that he's taking without having to think about modeling a human. But of course, it is possible to model a human too. I've encountered large training data sets collected by parties like Carnegie Mellon University from every Uber that's ever driven. So it is theoretically possible to create a reasonably trained model of what a human might do in given scenarios. And then, of course, this virtual control unit doesn't live in isolation. It actually lives on a network where it interacts with many other virtual control units. And so the idea here is not to do the full system simulation. But if you think about scenarios that are critical, landing, there's 6 computers involved in deployment of landing gear and ultimately successful landing. What can go wrong there? Braking. I think 3 to 4 computers are involved in this, and lots of messages. So this is what I mean by scenarios, not simulating the whole vehicle, but picking out interesting scenarios, right? And then, of course, this has to coexist with MATLAB Simulink, with UML, with hardware-in-a-loop systems, with real hardware. And then if you had a system like this, it would be really nice if you could actually inject faults anywhere to cause random failures, right? And so fault injection infrastructure would want to be able to have access literally to any construct inside this environment. And then you would want to do orchestration and coordination of faults. So multiple faults happen, possibly in particular sequence. And then beyond that, you could have test strategies where you can use field data, constrained random, or maybe algorithmic test synthesis to drive intelligent scenarios. And ultimately, this sort of boils down to, can we pound on this system to hit corner cases that are not naturally reachable or conceivable by human? So finding scenarios like the Air France crash or MAX failure in 737 MAX becomes realistic. I actually spent quite a bit of time talking with Boeing about this type of solutions. Anyway, so to conclude, I have a number of projects going on around EDA. In platform-based design, I have programs IDEA, POSH, ACE, RTML, and this includes automated creation of accelerators, runtime hardware software reconfigurability, and many, many other things. In system synthesis, we have ACE and IDEA that do automatic integration of IP into platforms, and system synthesis that optimizes for traditional economics plus security. And in advanced simulation, we have DITO, which is the reduced order model program that I mentioned earlier, POSH, and there's more to come. I have a major program under development in the Reimagining digital simulation space. And here we're going to do exactly the kinds of things that we talked about. But the point of a DARPA program and the challenge is to define what we're looking for and then step away from this. So DARPA is not going to tell the community how to solve the problem. My job is simply to articulate the problem in a way that the community can run with, and then prove to them that there's at least one solution to this. And then most likely, if people who propose my solution back to me typically will not get selected. So what we're doing here is we want to start a conversation that leads to interesting and different solutions. And then, of course, secure silicon, which is not a subject of this conversation, but I am speaking about secure silicon on Wednesday in a different session. So if you really haven't had enough of me, you can go and listen to me talk for an hour about secure silicon. So then the call for action to EDA community is there's a lot to do. Our startup ecosystem is broken. What can EDA do to help new chip design companies come into existence? What can you guys do to bring down the cost of working prototype so that it fits the worldview of private capital investors? And so that silicon companies are as easy to get funded as consumer web plays. And that would, I believe, improve the economics for US startups substantially. If there are any questions, I can entertain them now. If there are not, I will not be offended.
You must have known you could count on me, Serge.
Thank you, Brian.
You talked a lot about raising the abstraction from RTL, clock cycle accurate, up to the instruction accurate. The problem with that change in abstraction has always been that you are now not necessarily functionally correct with any simulation that you perform. Have you thought about or started looking at how do you test the sensitivity of that change in abstraction with respect to timing so you can find out how confident you are in those surrogate models? Because without knowing that, you really don't know how close to the actual functional simulation you still are. Second question.
Hold on. I'm going to forget the first one.
Okay.
So I think what I said is that we're sort of separating the design under test from the rest of the stuff. And so I think we can take liberties with the detail in a partition that is going to turn into a reduced order model. But the liberties we're taking are making the timing model more coarse. So, but to answer your question is no, not necessarily. We're not bringing those two worlds together because the objective that I'm trying to pursue is drastic improvements in performance. So the moment I have to start connecting low abstraction things into this whole environment, it defeats. If you still have one model that runs at 1 cycle per second, then the rest of the system that we put together is still going to be slow. So we're actually experimenting with some levels of heterogeneity in this context.
Okay. The other thing, a lot of what you're talking about is speeding up the functional verification. What about performance verification? What about power verification? All of the other things that may need actually completely different surrogate models.
Yeah, so I think that's a great question. So what typically happens is when we postulate the question like this and call for proposals, people come and propose adjacent things, just like what you just mentioned. And what I will do in this BAA, when it comes out, is I will keep it open like this. It's not just functional, so that people can propose against this adjacent problem sets that you mentioned. I totally agree with you. It's just that I need to streamline the concept in order to get it through the very narrow government approval funnel. And then the community, on the other hand, is not as restricted as me. People can propose anything that they believe addresses the broad goals that are stated. Thank you, Brian.
Hey, Serge, Mike McNamara. That model that you've abstracted up, I think of it as you moved the model closer to the sun, so it casts a bigger shadow. That gives you a model that you can now derive a more efficient implementation of that exact same behavior. I wrote a book about this with Brian on transactional level. If you can get up to the transaction level modeling, right, that is now an encapsulated what the functionality is that is divorced from the RTL, and maybe now you can get a much more efficient
But the ILA concept is higher level. It's
Correct.
It's beyond the TLM.
No, exactly. So the higher up you can go, then the wider you can reach to find a more optimal implementation that might, just be much faster than everything. So that's another, once you advance the state of the simulation using this, those abstracted models with some refinement, because they may have abstracted away some key bit that actually makes it useful. So you have to be able to put that back in, but that could be a new basis for you to find a more efficient implementation.
Thank you. Yeah, depending on how the timing lays out, we may do a request for information to the community and another workshop to subject this to larger conversation. But typically, the government process is so long that I tend to skip the RFI and the workshop process just to get things done more rapidly. But you know where to find me. Please, any of you guys, feel free. If you have any cool ideas that are worth contemplating in this space, feel free to send them to me.
Great presentation. My name is Prit Banerjee. I'm CTO at AMSYS. we do different types of simulations. The gas turbine example that you talked about is the type of simulation that we do. So we have been working on reduced order models for a while, and exactly using the approach that you said, right? So you have the engine blade where we do finite element analysis and type there. The difficulty that we face, and I think the community will face, is as you build these reduced order models, it will work for the specific case that you're training the data on. And it's like the AI models always work on the trained model. As soon as you give it a different case, it is very hard to generalize. So as you create the BA, I mean, first of all, congratulations, you are solving a really important problem. But we at ANSYS would be interested in if the community can sort of solve the problem of using AI models or ROM models to extrapolate based on data that they have not seen. That generalizability problem is a hard problem. But thank you.
Thank you. I expect ANSYS to be involved in this conversation once we get something out. But I would agree with you, and I think that if you look at third generation AI, where you train on very sparse data sets and infer things that you haven't seen, that may be one of the strategies to contemplate. People in mechanical have done quite a bit in this, and it seems to me like the mechanical problem is much more complicated than the one that we have in digital or even analog design. So with that, I'm going to have to close this up because I am on a panel upstairs, and all the other panelists probably presented their viewpoints, so I will have to respond to them now, not knowing what they said. Thank you very much for listening.